Now that we understand how El-Gamal works as an encryption scheme, let's jump right in and talk about its security. Why is this a safe thing to do? Now, this is our first public key system that we've seen in class, and it is still in use today, and it's used by some major corporations that don't like to gamble with their revenue. So it must be secure if they're using it. So let's try to understand that. Now, you know that El-Gamal is based on Diffie-Hellman, and so since we believe that Diffie-Hellman is secure, you should probably also believe the same concepts protect the security of El-Gamal. So let's start to understand this. So let's suppose that Alice has published her public El-Gamal key data as usual, and she has correctly hidden her private decryption key X, right? So her public stuff here has been made public, and her secret stuff has been kept secret. Okay, now we're going to assume that Alice has done her job correctly and she has set up her El-Gamal data with a very large prime modulus. So her prime P and her modulus is going to be at least a couple of hundred digits long, not some 5-digit prime, but much, much, much larger. And what that means is that a brute force attack is simply off the table. It's never going to work. It would take longer than the currently known age of the universe to brute force half of the keys, so it's just not going to happen. So let's take brute force off the table and let's consider the standard message attacks. Remember, there are 4 standard message attacks on any encryption scheme. Okay. So let's first look at the most basic baseline attack, which is known ciphertext. And this is the attack where Eve only has access to what is supposed to be public, namely the ciphertext, right? In any encryption system, you are supposed to have enough confidence that you can transmit your ciphertext over the open channel, and that's not going to be a problem. So let's see, is that true, right? So let's suppose that Bob takes a plain text message M, and he does the right thing and chooses a secret session key Y, and he computes B, K, and C as always. These are the same old formulas we always use in El-Gamal, right? And remember that the ciphertext that Bob will send to Alice consists of capital B and little c. K is not ever transmitted. So B and C are transmitted as an ordered pair, and Eve sees that. So Eve sees the message BC and nothing else beyond what is publicly available, Alice's key data here, the public key data, okay? So why doesn't this reveal too much to Eve? Let's see. What does all this data tell Eve? Well, she knows B, right? That was transmitted to Alice. And she knows G because it's public. And Eve also knows that Bob's secret Y, whatever it is, has to satisfy this equation that B is G to the Y mod P. So the question is, Eve knows B, she knows G, and she knows P. Can she solve for Y? And the answer is, well, no, not realistically, because Y is a discrete log. It's a discrete log of B. So this is a discrete log problem all over again. So from the public information of B, G, and P, Eve cannot derive the private Y because that is being secured by the hardness of, once again, the discrete log problem, which is exactly what we saw happen in Diffie-Hellman. Okay, so now you're supposed to be confident here that Eve cannot get Bob's Y. Okay, but there are some other secrets. For example, the plain text message M is supposed to be a secret. Is there a way for Eve to get M? Okay, well, Eve knows C, by the way, right? Because that was part of the ciphertext that was sent to Alice, right? And she knows that C is K times M, right? So she knows C, right? In order for her to get M, she must also know K, right? So she needs to know K. So she can't get anywhere to get M without knowing K, right? Because M, after all, is K inverse times C, right? So the question is, can Eve get K? Well, let's think about how K comes about, right? Well, K comes about in 2 different calculations. Once when Bob calculates it, and then once again when Alice calculates it. And these calculations are, for Bob, it's A to the Y, and for Alice, it's B to the X, right? So in order for, let's say, Eve to get K from doing Bob's math, she would need to know Y, but we just argued she doesn't know Y, right? What about Alice's math? Can Eve get the key K from doing Alice's math? Well, to do that, she would need to know X. She needs to know B to the X. She needs to know the X part. And of course, that's secret. So the question is, well, can she get it? Can Eve somehow get X, which is supposed to be secret? Well, amazingly, it's exactly the same story, right? Because A is public, so she will know that. Eve will know A. Eve will also know G, and she'll know P. And she also knows that Alice's secret X comes about from A being G to the X mod P, where she knows A, G, and P. So look, the question is, can she get X from that, right? So she knows A, G, and P, and she would like to get X. Well, no, because that is once again a discrete log problem. To solve for X up here in this equation would be to solve the discrete log problem, which no one can do. And so hence Eve cannot get Alice's X, and so therefore, as a consequence that she can't get the X, she also can't get the key, the affine key K, and because she can't get the affine key K, she also can't get the plain text. So this thing is secure against the most basic sort of attack. And please note that this is exactly the same discussion we had with the security of Diffie-Hellman as it relates to the discrete log problem. So the discrete log problem is central to cryptography, and it will not be the last time we see it. We're not done with it. So thus it is the discrete log problem that safeguards both Diffie-Hellman key exchange and El-Gamal from this sort of attack. Okay, so let's take a break and we'll look at the next message attacks in the next lecture.